Hello, welcome back to the urinary system videos. And the last time we talked about the glomerular filtration membrane and the different processes that are going to occur in the nephron. So we're going to now focus on some specifics about glomerular filtration. So that was what was going on in the renal corpuscle. So we're going to talk about how things get filtered, what are the forces that are causing that. And then we'll see with this video if we may be able to get to how that process is regulated. So to maintain our blood substances at the right amounts and get rid of waste products. All right, so I'm going to go to our picture. Okay, so last time we talked about the filtration membrane. It was made up of the wall of the glomerular capillary, and then little foot processes of the podocytes, and so they had little filtration membranes. So this image, I didn't show it in the last video, but it kind of zooms in on the filtration membrane, so you can see the different layers, and then you can see the components of the blood here. And some of the components will leave the blood, but again, it's mostly the plasma components, except the big proteins. They're too big to get through there. So also there's a negative charge as well, and so a lot of proteins have a negative charge, so that kind of prevents them from wanting to go in that direction too, because they kind of repel each other. So all right, and then there's another picture. You can see the fenestrated capillaries and the podocyte with its little filtration slits. All right, so that is at our, there we go. That is all happening here at the renal corpuscle. So with the glomerular filtration, this is the filtering of the blood that's going to allow for our rest of our nephrons to determine what needs to stay in the blood and how much and what needs to go in the urine. So it's really important to maintain filtration at a constant rate. So we want to make sure that the amount that we filter each minute stays pretty constant. Because if we don't keep it, moving at the, a normal rate, if it moves much more slowly, then things that we don't want to stay in the blood are going to stay in the blood, like waste products, and they can be toxic to our cells. And then the opposite is if we do have the filtrate being produced at a much faster rate, you get more filtrate. It moves much more rapidly through the tubules, and there's not a lot of time to reabsorb the things that we need. So we'll lose a lot of stuff in our urine that we actually need. So we want to make sure that this process of filtering the blood in the glomerulus or renal corpuscle stays at a steady rate. So these are the pressures that are involved in keeping that rate of blood being filtered at the glomerulus. And so we kind of already talked about these pressures when we talked just about the continuous capillaries and how they exchange at that level, how we get exchange of nutrients and oxygen and carbon dioxide and waste products between the continuous capillaries and various cells of the body. So the same pressures are going to apply here. So hydrostatic pressure, colloid osmotic pressure are going to be the forces that are keeping the production of filtrate going. So in a steady rate. So this is the hydrostatic pressure of the glomerulus. So in these little capillaries, remember I said in the last video, there's actually a higher blood pressure or pressure within these glomerular capillaries. So normal capillaries that are allowing for exchange of nutrients, oxygen, waste products, and carbon dioxide, they're like 20 to 40. So they're a smaller amount of pressure in those. The glomerular capillaries are about 60. So we keep the pressure in the glomerular capillaries at about 60 millimeters of mercury. And then I think this is an objective later, but I'll go ahead and explain how it stays at 60, or at least one of the things that contributes to it, to the pressure in the glomerular capillaries staying at 60 millimeters of mercury. If you look at the afferent arteriole, you'll notice that it's more dilated compared to the efferent arteriole, which is more narrow here. So that is one thing that helps keep the pressure higher. If these were the same diameter, we'd have kind of the same amount of blood flowing in as flowing out. And then we would have like a lower pressure within these glomerular capillaries, maybe closer to the 20 to 40. But we don't. We have more blood coming in to the glomerulus because we have this less resistance here. It's more dilated. And then we have more resistance going out, so that kind of slows the blood from leaving. So that allows for the pressure within the glomerular capillaries to be higher and at the pressure that we need them to be to force the plasma and its components out. So it's at 60. So that's forcing the fluid and all the smaller substances that can get out. So remember, the red blood cells, white blood cells, platelets, large proteins, they stay in the blood because they're too big, but everything else is going to leave. Now there is, since we're producing filtrate, there's generally always going to be some filtrate in this capsular space. So there's a little bit of pressure, very, a lot less than what's in the glomerular capillaries, but it's still a pressure that's kind of opposing the movement of fluid and plasma components out. And so we call that hydrostatic pressure of the capsule. So it's pretty low at 18. All right, so then the other pressure that's also opposing the movement of substances out of the glomerular capillaries is the colloid osmotic pressure. So that's what the OP stands for, colloid osmotic pressure. And so remember, we just said the proteins stay in here. And the proteins, and other substances too, but mainly the proteins, form that higher solute condition in here. And so that always attracts water. Water wants to move from an area where the solute concentration is lower to an area where it's higher. And so we do have that colloid osmotic pressure wanting to draw fluid from the capsular space into the glomerular capillaries too. All right, but realize that we call it the net filtration pressure. So that's the difference in these pressures. So the one that's the ones that are opposing each other. So we just take 60 minus 32 minus 18, and then we get this net filtration pressure. So that's the pressure that's required to produce the filtrate, push the plasma components out of those glomerular capillaries, and form that filtrate. And if we keep these pressures at these levels, then they do that at a certain rate. So we produce so much filtrate per minute so that we can maintain that filtration rate, which is important for our bodies. Okay, so that is our defined glomerular hydrostatic pressure. Explain why it's higher. So that was in the subjective. I thought it was another objective. So explain why it's higher than the pressure in the capillaries. So that's because the afferent arteriole is more dilated, allowing more blood to flow in there, and the efferent arteriole is more narrow, allowing the blood to flow a little more slowly out of there. So that helps. Name the two pressures that oppose it. So that would be the colloid osmotic pressure of the blood and the hydrostatic pressure of the capsular space. And then again, you'll get your net filtration pressure if you just take the difference between the glomerular hydrostatic pressure and the two opposing pressures. All right, so we have some time. We can maybe talk about the glomerular filtration rate. So this is the parameter that is kept in a narrow range in order for us to filter the blood and get out the stuff we don't need and keep in the stuff we do need. And so our body has some mechanisms that keep that glomerular filtration rate at a constant level. And then we'll talk about factors that influence it too. So glomerular filtration rate. Aha. All right, so the glomerular filtration rate is just the volume of filtrate that's produced per minute. Usually that's how they'll state that is, the glomerular filtration rate is how much filtrate we produce, like the volume, so milliliters per minute. And again, the body wants to keep that in a narrow range. And if the body's able to do that, then we get all the waste products that we need out of the blood, and then we keep anything that we need to be in the blood for our cells, keep it in the blood. So, all right, and so the glomerular filtration rate, you can imagine the net filtration pressure. It's going to be, if it goes up, then the glomerular filtration rate goes up. If it goes down, the glomerular filtration rate goes down. So they're directly related to each other. So, and we talked about this earlier. So if we have a situation where the net filtration pressure goes up because we have some sort of changes in these pressures. So if we, develop high blood pressure, or if maybe we lose some proteins in our blood, that would change these numbers, and that would change our net filtration pressure, and thus our glomerular filtration pressure. So if we have a situation where the net filtration pressure decreases, that's also going to decrease our glomerular filtration rate. And if the glomerular filtration rate decreases, that's going to cause less filtrate, and we're going to not be able to filter all the components out of the blood as well. And the big thing is, kind of the first thing that's going to cause some problems is the waste products that stay in the blood are going to start to increase in amounts, and those are toxic to our body cells. So they will have an adverse effect on our body cells. So that's what's going to happen if we have a decrease. And then if we have an increase in glomerular filtration rate, because net filtration pressure increases, then what we'll have is we'll get a lot more filtrate produced. And that fluid, because there's more, will flow much more quickly through our tubules, and there'll be less time for reabsorption of substances, and we'll lose more in the urine, things that we actually want to keep in our body for our cells to use. So they have a little diagram here that kind of shows what happens if we have an increase in net filtration pressure, which will increase our glomerular filtration rate, which is how they abbreviate it, GFR. So know that that's going to increase the amount of filtrate, the solutes and water in the tubular fluid. They're going to remain there and go into the urine. So we'll get a lot more things in the urine, substances that we actually wanted to keep in the body. And then if we have a decrease in our glomerular filtration rate, then we're going to have the buildup of waste products in the blood, and then our filtrate reabsorption will decrease as well. We won't have as much to reabsorb. So, all right, so that is our 14 through 16 on the glomerular forces in the glomerulus that caused the filtrate to be formed, and the glomerular filtration rate was just a parameter that our body wants to keep in a normal range so that our cells remain happy. So the next video we'll talk about 17, 18, and 19, which talks about how the glomerular filtration rate is regulated. So so no matter what's going on in the body, there's some mechanisms that are in place to keep the glomerular filtration rate in that normal range, so that we can continue to keep what we want in the blood and get rid of the waste products and things that we don't want in the blood. So that'll be the next video. We'll talk about those.